In this screencast, I'm going to talk a little bit more about Faraday's law of electromagnetic induction, and I'm going to review some of the examples in the second half of the chapter in sections 18.6, 7, and 8. In each one of those sections, they have examples where they vary one of the variables that affects the induced EMF caused by a change in the magnetic flux. So I guess what I'm going to do is I'm going to go over one of the examples where the area changes, which is the example in 18.7, and then I'm going to talk about when the orientation changes, which is in section 18.8, and that is the example there is the induced EMF that's created by a rotating loop in the presence of a magnetic field. It's basically an electric generator. So that is really important because that's how our electricity is generated for our homes, and I want you to understand a little bit about that. So let's just review real quick as an introduction to the screencast Faraday's law. We have the induced EMF, and of course an EMF is just a potential difference. Instead of being across the terminals of a battery, it is caused by, it's caused by the changing magnetic flux through a loop. And so it's measured in volts just like a potential difference. So don't be confused by the fact that it's an EMF. It's just a potential difference that is induced instead of caused by separated charge in a battery. And it's directly related to the number of turns, of course, in the loop, in the solenoid, if you will. And then I'm going to use the book's notation for the absolute value in the change in flux over a period of time. And of course, we know that the change in the flux can be, the change in flux can be expressed as the intensity of the magnetic field times the area times the cosine of the angle between the normal line of the area and the magnetic field itself. Okay, so that's what flux is, and I should have a delta in front of all of that. So it could be any one of those things changing. So let's talk about the example in section 18.7 first, which is the changing area. And the example that is given in your textbook is where there's a loop. Basically, it's an electrical circuit, and it's shown here in this picture here. It's a wire that's got a metal conductive rod that's in electrical contact with the wire, and the rod is being moved to the right at a velocity of 6 meters per second. And it's in the presence of a magnetic field that's going down the page this way. There's your B field. And attached to the circuit is a light bulb, which acts as a resistive element. It's a 10 ohm bulb. And it gives you all the information up here for this circuit. This is a pretty common type of problem in where an area of a loop is changing, and it's actually a circuit that is connected by this rod across here that's allowed to move back and forth. Since what it's asking for is the direction, the magnitude, and the direction of the induced current right here. Magnitude of the induced EMF, and the magnitude and direction of the induced current. Direction of the induced current and the magnitude of the induced EMF. All right. So as you can see here in the sketch up to the top right, the external B field is into the page. So as you slide this bar to the right, the number of B field lines, the flux is changing, it's increasing down into the page. So Lenz's law says the current that's going to result wants to oppose that change. I always think of it as the whatever B field lines are going through the loop initially, the loop doesn't want that to change. So if you increase them going into the page, the induced EMF is going to oppose that by creating a B field that goes out of the page. So using your right-hand curl rule, which is the magnetic field right-hand rule, you're going to point your finger up so that the thumb is pointed up here on that bar, so that your fingers curl around and point out of the page to oppose the changing B field into the page. So the current's going to go counterclockwise on this. So that's the direction of the current. The magnitude of the current we can figure out based on the equation for Faraday's law. So if we go to this next page here, the induced EMF, the number of turns is just 1 times the change in the flux per time. Well, that's just B times A times cosine theta. Cosine theta is 1. And the area, so they moved B outside, the B external outside the absolute value brackets there because it's constant. The area is just length times width. So the area is the length of the rod times XF minus XI, which is the changing position of the rod horizontally. Since the length of the rod's not changing, that can come outside the absolute value symbols. So it's just the displacement of the rod horizontally divided by time, which is really velocity. That's the same result that we got in class a couple days ago. So it's just the external B field times the length of the rod times the velocity of the rod to get the induced EMF. That's going to give us the magnitude of the induced EMF. If I want to know the magnitude of the current, I've already determined the direction of the current, I have to use Ohm's law. So Ohm's law takes the magnitude of the induced EMF, which is that, dividing it by the resistance in the bulb, which I think is a 10 ohm resistance. Yep, that's up here, 10 ohm resistance. And we can find the magnitude of that current is going to be 0.14 amps. So you can either use I squared R or V squared over R to find the power dissipated by the light bulb. Since we just found I here and we know the resistance in the bulb, we can just square I multiply times the resistance in the bulb and find that the power output is pretty low, 0.21 watts. Okay, so that is an example of a single loop, N is 1, and a changing area in a constant magnetic field. Let's talk about a more common, I guess, thing because it's relevant to our everyday lives, and that is an electrical generator. This is a very simplified electrical generator. And I say simplified because it's a single loop. It's a single loop that's rotating in the presence of a magnetic field. The magnetic field lines are going across this permanent magnet from left to right, and I call it a permanent magnet. It could be an electromagnet. There could be a magnetic field created by an electrical current, but it's shown in this drawing as a magnet, north pole on the right side, south pole on the left side. So what's happening is you're taking some natural gas and you're or it could be propane, probably natural gas, boiling some water in this example, creating some steam. You increase the internal energy of the steam by heating the water, by turning it into vapor, and then you superheat it. It turns into super high internal energy steam. It turns this the blades on this turbine, and when it does that, it loses some of its internal energy. So obviously by turning this internal thermal energy into mechanical energy, energy is conserved. You're just transforming it from one form into another. And when you turn it, this loop is attached to that. So you got this loop here, this electrical circuit that's attached to the rotating turbine, and it's spinning in the presence of a magnetic field. So you've got a conductor spinning in the presence of a magnetic field, so there's a changing flux. The changing flux is caused by changing area. And the changing area is when this loop rotates. It goes from being perfectly parallel to perfectly perpendicular as it rotates over time. So we have to kind of develop a way to analyze this, and I'm just going to give you an overview of what's in the textbook. First, I'm going to give you a little brief review of rotational kinematics because your textbook uses some rotational kinematic variables to explain this, and I want you to be able to understand that. I don't know if Mrs. Macaulay covered rotational kinematics in honors physics, and I think she probably did. I know we did it in AP Physics 1, but I just want to give everybody an overview because it's been a long time since you've seen these variables. Okay, if you remember, there's 4 kinematic equations in the linear world, and I'll just write out the most common one. Sorry, my writing is so sloppy here. The most common one that we use most often looks like this. Delta x equals initial velocity times delta t plus 1/2 acceleration times, I guess I should be consistent, delta t squared. That's a linear kinematic equation. And then, of course, velocity average equals displacement divided by time. Remember that every variable in the linear world has an analogous variable in the rotational world, and instead of measuring linear distances or linear displacements, we measure angular displacements, and by angle we measure in radians rotationally. If you remember, delta x's counterpart was a change in angle in radians. It was delta theta. And instead of velocity average, we had omega average. That's rotational velocity. This is measured in radians. That's an angular measurement. This is measured in radians per second. Okay, and the equation that you're going to see on in the next page when I flip over, it's solving this equation for displacement. So if you solve this for displacement, you get delta x equals average velocity times time. But if I assume my initial position is 0, then I can just say x equals average velocity times time interval. The rotational analog to that is the angular position at any moment in time is equal to the constant, because our little blade is going to be, our turbine is going to be rotating at a constant rate. It's going to be our angular velocity times time. Okay? So that's the equation you'll see on the page. This is a picture of a shot from your textbook, and it talks about how you can understand a little bit more about how this rotating loop, how we can describe this mathematically and better be able to understand the induced EMF caused by an electrical generator. It starts off, It starts off with an equation for magnetic flux. The external B field is constant in this case, times the area, times the cosine of the angle. Cosine of the angle is what's changing. So your textbook talks a little bit about these kinematic equations in the rotational, with a rotational notation. And here's that equation that I mentioned on the last page. So we're going to take omega t and substitute it in for theta here, because we've got a constant angular velocity omega of this little loop rotating. So the flux at any point in time is just equal to the external B field times the area times the cosine of omega t. Again, that's just theta. Now it turns out the induced EMF in Faraday's law, we have to have the changing flux with time. So we have to take the derivative of this with time. That's a calculus term. If you're not taking calculus, that's okay. But in order to understand the derivation of this expression down here, you have to understand how to take the derivative of this expression right here. You don't have to know how to do that, but it's easier if you know calculus to understand where this came from. The cosine omega t, the derivative of that is omega sine omega t. The omega comes out in front and the cosine turns to sine. So this is the equation for the induced EMF in an electrical generator. Now what's interesting about this is that gives you the equation. If I wanted to graph induced EMF versus time, it's going to be 90 degrees out of phase with the flux as it varies with time, because cosine and sine are 90 degrees out of phase. So I'm going to show you this little graphic over here on the left on the next page, and that's really what I want you to get out of this. This whole derivation on this page, if you're a little fuzzy on it, that's okay. If you don't remember your rotational kinematics that well, that's not the gist of this. What I really want you to understand is on the next page. So let's take a look at that. This graphic right here is kind of a top view of the loop as it rotates. You can see it's rotating clockwise. Here it's in kind of a vertical orientation. It's rotated 90 degrees here, so now it's horizontal. Now it's rotated 180 degrees from the first shot. Now it's 270 degrees from the first shot, and here it's back to where it started. So it's like one full rotation. And here it shows the flux as time changes. Notice that you've got maximum flux when the loop, the area vector, is parallel, the normal vector from the area is parallel to the external B field. That occurs at that location and at this location. Maximum positive, maximum negative flux, and then back to maximum positive right here. These points here where the area vector is perpendicular, that would be cosine of 90 degrees in the expression for flux, and that's cosine is 0, so you don't have any flux at those 2 points. The thing that's really interesting is if you look here at the induced EMF, the sign is negative, that's Lenz's law, so the induced EMF creates a current that opposes the change in the flux that created it. So whenever flux is maximum, we're talking about slope here, you have to look at the slope of this graph. Slope of this graph is this graph down here. So the slope at time 0, the instantaneous delta phi delta t is 0, so you'll notice the induced EMF is 0. At the location of maximum negative slope, which is right here, you have maximum positive EMF. So a negative slope, because of the negative sign right here, equals a maximum positive EMF. Down here where the slope is 0, we're back to a 0 EMF. Where you have a maximum positive slope right here, you have a maximum negative EMF. So again, slope of this graph is the value on this graph down here on the bottom. So that is probably the most valuable part of understanding the induced EMF as it changes. And notice these are 90 degrees out of phase because this is cosine theta, this is sine theta. So they're 90 degrees out of phase. Hopefully that helps. If you have questions, just so you understand how the generator works, it operates on the principle of a changing area over time, and the B field is constant. And it does rotate at constant speed. In your houses, the current changes direction 60 times a second. If you notice here, the induced EMF changes every cycle twice. So it goes from 0 to positive, back to 0 to negative. So every time, the direction is going to change twice every rotation. So you've got 60 hertz alternating current coming out of your outlets in your house because of that rotational motion happening back at the electrical generation station. So if you have any questions, ask me in class or stay after or before class. Okay.